Okay, so we'll start from where we left off. To recap what we did overall, we studied at the start different use cases in different verticals. We studied overall dimensions of what unsupervised versus supervised learning was. Then in supervised learning, we discovered briefly the role of training and testing data. Then we went on to understand that within supervised, we had two kinds of models. One is classification, another was regression. Classification is about identifying a set of classes to which the target output should belong. Regression is about a function mapping from input to the output. Then we went on to do more serious algorithms. We started with unsupervised learning. We covered two main categories of algorithms there. First one was clustering. The second one was association rule mining. In clustering, we saw how k-means clustering was giving you an approach to keep all related observations in one cluster so that they're separate from all other clusters. Then we saw how K can be determined by using a incremental approach of bottom up and then drawing up a dendrogram and fixing a K at the right level. Then we saw association rule mining, which is another form of unsupervised learning, which basically looks at how we can discover co-occurring things. It could be in retail, like what people buy together, or it could be a whole set of symptoms which occur together in case of healthcare, or it could be in case of crime scene investigation. It could be what are the calls made together, or who are the people who are accomplices. This kind of scenarios. Then we started exploring supervised learning. Supervised learning, as the name implies, involves an element of supervision. There is an explicit notion of a model. It could be a set of classes or a set of equations or a function describing the target model. Then you change the model such that you work with part of the data, which is 80%, say test train data, find a model, then test the effectiveness by means of the predictability of the learned model on new data. That is where you create 20% test data and test on it. You find out what kind of error could be there, or what we say in machine learning parlance is what is the bias variance trade-off. So bias variance trade-off, when you say, there is two notions. One is bias with respect to the current sample. What is the dependence on the model you learned for the current sample? That affects predictability. Variance is another dimension where you say that if for different data sets you're getting different models, which is very different for each data set, then it's not a good idea, because that means you're not basically learning any standardized model. So usually there is a compromise between bias and variance, and we really would like to have a balance so that we have a robust model which is reasonably general, representing of the data in the whole population. At the same time, we want something which is able to give you a prediction capability for the future. So supervised learning actually has several forms, several algorithms, decades of research. In fact, my personal view is that probably there is a lot more, research done in supervised learning. Unsupervised is just about taking off because we are working with large machine learning algorithms and large clusters, just about to start with. And why we want to look at both in a balanced manner is because for the future, it's possible that with the deployment of large clusters by Google and all that, we will see large strides in areas like neural nets, deep learning, etc., which can do more effective unsupervised learning. So the third element of unsupervised learning, which I forgot to mention, is the feature recognition, right? Where you talked about taking a set of videos or images, understanding it as a set of features, and how we can extract features from large corpus of data without prior knowledge of what a collection of what a cat is, what a dog is, what a man is, what a flower is. Well, that becomes a discovery process. So when we are on the topic of supervised learning, yesterday we briefly covered what a Bayesian method is about. So there are several variations of the Bayesian techniques in usage in machine learning from a supervised learning perspective. But important thing for us to understand is we will be looking at a scenario where we usually have prior probabilities or normal probabilities of any event, which is what we call a priori probabilities, means independent of comparing with any other condition or event. That's what we call as a priori probabilities. So look at this example on the slide. We talked about two scenarios. Either it's raining or it does not rain. Normally when it 60% of the time it does not rain, 40% of the time it rains. So probability of it raining is 0.4, probability of it not raining is 0.6. Now we also would typically like to understand relation between two events. That is where conditional probability comes. So what is conditional probability? We already saw previously. Probability of conditional probability of say condition B1 A is what is the probability of A and B1 happening both together divided by probability of A. So that's a conditional probability. That means that it is the probability when A has already occurred, and then you want to find out the possibility of B1 having occurred. That's the idea. So it is important for us to understand that this notion changes the notion of probability from an absolute a priori probability to something which is dependent on another event. So that's why conditional probability becomes important. So when we talk about conditional probability, in this condition, let's talk about a new event, a wet garden. Now, in case of a wet garden, it is, suppose we have conditional probabilities which are known beforehand, saying that if a condition of rain has happened, condition that it will be a wet garden given that rain has happened is very high, is 90%. Same way, if it has not rained and we want to find out the probability of a wet garden, it is 20%. Naturally, it's expected to be low, right? So now if you want to say what is the probability that it has rained given the observation that it is wet garden. So that is what we mean when we say Bayes theorem is applied. So what does this do? It basically gives you the formula by which you can work backwards of a past event having observed a phenomena. So generalize this to several scenarios. Put on a business hat. What do you want to look at? What do you want to look at it in business terms? It basically means you look at an output or an event that has occurred. Now there may be several causes for that event. Let us assume you have two causes, 1, 2. So what you want to say is, having observed that event, the probability of that condition, one of the condition is, given that the event has occurred, is measured by the relative conditional probability of A given B1 has occurred times probability of B1 divided by multiplication addition across all such possibilities. In our case, we have only two possible causes. Either it is rained or it has not rained, right? So that is what is basically gives you the prediction capability or classification capability for machine learning in terms of Bayesian application. Usually you have prior probabilities for individual causes. You have conditional probabilities of the effect given individual cause. Now you have to find out that here is the effect, here is the symptom. What is the probability that it is caused by this particular cause? So think in that direction. So think in terms of causality. I will take you a bit forward today. I will come back to the yesterday's example of detailed classification of the example, but I want to carry this concept of causality. So basically, if you look at this notion of causality, it's about there are several causes, one effect. Here it is rain, not rain. Not rain, let's equate it to something like a sprinkler. So you can say it's rain or it is sprinkler. So it is 80% this, 90% this, sorry, 40% rain, say 40% is probability of rain, or 40% normally it does not rain. So possibly you can equate it to something like that. Now, when we have a notion of a set of ground level data, which is instances, right? Each row is a collection of values for independent variables, and there is a observed output class. So think of it how it is different from the previous case where you were doing clustering. There was no notion of an output variable in the previous case. Here you ultimately have an output variable which is specifically a what we call as a class variable. We saw yesterday in the tool also, which can take any of the m values. So in the previous data which you already have labels saying that this belongs to class 1, this belongs to class 2, this belongs to class 3, like that. So what we need to understand is output class is usually a specific type. In some cases, it could be a discrete 0, 1, whether some something is yes or no. In some cases, it could be a continuous variable. It could be like a functional value, which is saying that so and so real value. So there could be different varieties of classifications you can do. So in the continuous case, you can say that this range probably falls under this class, or in the plane, a section of this plane divided by these lines forms this class. So important thing for us is to differentiate from the unsupervised learning in multiple ways. First and foremost, there is a separate output variable. Second, there is a notion of labeling of the data items in the existing past data, where you explicitly label the output value to belong to specific class before you feed it to any machine learning algorithm. So what is the idea here when you are saying you want to do machine learning, you basically say that if I get a new data item, which is all the input variables instantiated with some value, like we saw yesterday in the case of you know the exam, right? What we need to understand is what is the output class? Is it going to be a class 1, class 2, class 3? So you have to, for that instance, what is the class you have to predict? So that's what Bayesian classifier also we're going to do. What we look at is if there are m different classes, we try to identify the possibility that this particular instance, let's call it X, which is a new instance which is not present in your past data. Let us calculate the conditional probability of each of these classes given the observation as per this new data item, which is collection of x1, x2, x3, x4, etc., which is the new data. Then find out which class has the maximum probability given that particular observation row. And then you assign it to that class. That is the idea. So in terms of prediction capability or new classifying a new data that is coming in, it uses internally the Bayes rule, Bayes theorem to identify which class has the maximum probability given the observation corresponding to values assigned for that particular row. But here there is one element which yesterday we kind of overlooked but we made use of, which is very important. If you look at yesterday, we safely said for the data row, age less than 30, income median, student equal to yes, uh, credit rating equal to fair. When we want to find out the probability of classification of the computer buying yes, then we safely multiplied individual conditional probability with respect to each of the attribute. Age equal to less than equal to 30, 0.444, 0.6667, etc. So what is that? That is what we're talking about in the previous slide, which is what I forgot to mention. When we say we are trying to multiply the conditional probability of individual feature or individual variable having that particular value in that row, and we're trying to multiply all of that, then this is basically giving you a notion that all the variables, whether you're talking of age, whether you're talking of income, whether you're talking of student, or whether you're talking of credit rating, all of them are conditionally independent. That is why you're able to get a plain multiplication of the individual instance probability of x1 given c1, x2 given c1, x3 given c1, x4 given c1. So in our case, let's take example of c1 is a computer buying it s. So we can multiply the conditional probability of age less than equal to 30 given computer equal to yes times income equal to median, which is the instantiation of second variable given computer equal to yes, times student equal to yes given computer equal to yes, times credit rating equal to fair given computer equal to yes. This is very important. This is notion of conditional independence And typically what we make an assumption here, this is a very fundamental assumption in all machine learning algorithms, is when we discover such features or different variables which are supposed to be independent, so we make a standard assumption, which is that they are independent conditionally and they are identically distributed. That's known as IID, independent and identically distributed variables. So we say that the age feature is independent of income feature, is independent of the student feature, is independent of the credit rating feature. So this notion is very powerful because this notion carries across in several classifiers or several supervised learning algorithms, because the attempt when you try to discover what are those influencing variables which are potentially going to cause an effect, leading to an effect, if you have large number of independent variables, it's very difficult to compute. Computationally, it becomes difficult. But at the same time, from the data, a lot of times you may come up with variables which are interrelated. Let us take example of, like, let us introduce a new variable in this. Suppose there was a data like, is he a poor student or a, what you call, a rich student? Is still a student, but that assume that poor or rich actually didn't make any sense, but it's only a student which is making the difference, whether he's a student or not. But you have an additional variable to deal with in order for all our equations or classifiers, etc., without any value add. That is where you have to do the appropriate analysis from your domain. If there are a lot of variables and you see dependencies between the variables where one can be deduced from the other, it's usually not a good idea to include the additional variable which does not add any value because it's not independent of the others. So in machine learning, it's very important to understand that whenever you're doing a classification or a regression and you're selecting all the independent variables or features and trying to explain the output with respect to the independent variables, you have to take into account the notion of what is a fair, what you call, judgment of independent and identically distributed set of variables. If you find any set of variables, two or three, which are such that they are dependent upon each other, if there's an equation between, say, x3 equal to x1 plus x2, there's absolutely no reason for you to carry around x3 because it's independent of, it's not independent, right? If you have x1 and x2 independent, you can actually compute x3. This is a very powerful and important element which you have to take into account, because the modeling of all machine learning algorithms is based on this very fundamental assumption of each of the variable being independent and identically distributed. So now when we do this, we are able to make very simple independent computation of what is the conditional probability of each individual variable, like say age, carrying out that particular value which you are concerned about for that row, then multiplying across all the four. That gives you the relative, so the conditional probability of basically the row having observed that you have computer bot yes or computer bot. Now, when we compute this across all the different classes, then you find out which class is giving you the maximum value. You understand? In this case, if you look at for the particular new row which we gave, age 30, age less than 30, income medium, student yes, credit rating fair, this is a new instance that's come to you. You find that The potential that this belong to class which is computer equal to yes is higher, which is 0.028 than computer equal to no. So we assign that particular row to a class by computer equal to yes. So here you have a very simple approach which is based on the number of occurrences of instances corresponding that is giving you the measure of the probability. So this conditional independence carries forward in much more interesting ways. So this is more from, we looked at it from a perspective of basically building a naive classifier for any new instance based on the